So welcome to this lecture number 4 of this module, and this will be the last lecture of this module. In this lecture I will discuss the various dampers those are used to avoid the voltage oscillations, current oscillations, and also sometimes line current oscillations, which I will discuss here. Last turn I was discussing about the DC reactor, and we can calculate what should be the value of this inductance value, that is a DC smoothing reactor, so that we can avoid the commutation failure. I will give one example in this class based on the several assumptions, and the assumptions are that the DC voltage is constant at its initial value across the inverter side. This voltage, AC voltage at inverter terminal remains constant. Tap changer does not move, means there is no tap changing is occurring. Initial current was IDN, and the collapse of the voltage, I am talking the DC voltage, occurs simultaneously with the beginning of the commutation. I mean to say that, you know, this is the inverter side, this is the commutation voltage of valve 3, where we are just giving here a signal, the beta, that is advance angle, with the certain here the margin, here I can say gamma. So at this point, when we are assuming all these assumptions, that once the beta is calculated, and the beta can be calculated is the expression, if you remember, this was your using ID, here IS2, here cos beta minus cos gamma, or reverse one.
Cos gamma beta.
Because this value is less than this, it will be cos gamma minus cos beta. So with this expression, normally for the given value of this, we can calculate the beta. So once the beta here is calculated, we are assuming that the inverter side AC voltage, means your EM, is your constant. It is throughout. At this point, it is said that the DC current before that firing, it was the constant in the link. Now here once you are firing, now there is a collapse of the DC voltage in the line. Then what will happen? The current will rise, and current will rise here, and this will lead to your another value of gamma, and that will lead to your commutation failure. So here this, it is said the initial current here, it was the normal current, IDN denotes the normal current, which was flowing in the DC link. So it is a constant here initially IDN. From here to here, once it is going to here, it is changing, and we are assuming is a linearly changing. And AC voltage, which I said here, the inverter side AC is not changing. Why? Because this calculation and other calculation, we are going to assume this is a constant, because this is nothing but your IS2. Sometimes I was using IS3 also, but the meaning is same here, under root 3 EM divided by twice omega L. So L is constant, frequency of the system is constant, and EM is, we are assuming constant, means this value is constant. So, and your DC voltage is a constant at is here, the DC voltage is constant. Now the DC voltage is going to, at this, the last assumption is that the voltage collapse is occurring here when it is going to just conduct at the beginning of the commutation. Here the commutation is going to start between the valves. So with this assumption, now I want to derive what should be the value of LD, that is a smoothing reactor, so that we can avoid the commutation failure. And for this, here see what we do. Normally here I can say now IDN is the normal current which was flowing in the beginning. This was calculated your N, and this was your N. It was the normal N. Here I am talking, this is your N value. Means we are firing at this, it is the commutation was going to take. If the DC current is a constant, there is no voltage collapse, it will be here concluded, and it will be N value. So for this value, given value, we can calculate your beta N. What will be the normal value here? We can calculate. Here we were always calculating the beta N, because we are operating in the CA mode. This value, we are just deciding what will be the CA, and this value will be the minimum value here, that is sometimes we fix it, it is called gamma M, that is minimum value. means we cannot go beyond this because commutation will not occur, failure will occur. So we can go up to this point, beyond that commutation failure will occur. So this is a some value, always this minimum value is, let's suppose 5 degree or 10 degree, so always it happen we fire in such a way that we can, commutation is over before, well before this. Now since there is some voltage collapse, current will increase, this value will exceed, and once it is crossing or here, the possibility of the commutation failure will occur in the inverter side I am talking. Now, so it is, as I said here, our current is at this value, your current is your IDN. Now the collapse is going to happen. Now this value here, it is your IDN. We are assuming that it can go up to here. The current is rising and the U will increase, it will be not commuted here. With this value here, it will, the beta is calculated for this one if ID is a constant. But it is changing, so it will be exceeding, and here some this current, and there will be some change in your ID current here at this M value here, gamma M. And it is assumed that the current is linearly increasing, so we can say, you know, this DI here, DN, not DN, we can say any current which is changing here, that is here I can say IDN if it is very small, dt, it will be nothing but your, this is a L1 upon LD, change in the dV over dt, or change in the time. You know, the change in the voltage is a LdI by dt. This concept we are just checking the linear one because the time duration is very, very small. It is in the less than millisecond. So from here we can say this LD, that is the inductance that is required, because the voltage is going to collapse, let's suppose it's 0. This inductance value must take care of if this value is taking, so this will be continuing and there will be no commutation failure. So this principle is adopted. So this LD here we can say it is, we can write here, it is your change in here voltage here into your dt divided by your change in ID. Here I think it is not this, here it will only Vd, because change in the Vd is your L di by dt. Yeah, it is not dt here. So this is, this value is there. So this is your inductance value we can calculate, where what is your delta t? Delta t is the time from here to here. From here to here we are assuming this is the delta time where the commutation should be finished without avoiding the commutation failure. That's why it is written here beta n minus here gamma m. It is not gamma n. Divided by here this omega. And this value will come, if we are taking this as a in radian, then it is in radian, otherwise you have to, here you have to 2 pi, you have to write 360 degree. If you are using the betas in degree, then instead of here omega 2 pi, you have to write 360. Otherwise it will be, if you are using radian, then it will be 2 pi is okay. So this will be divided by 2 pi f, f is the frequency of the system, where these values are in radians. If you are using in this angle, so this beta n, now I can write angle, gamma m angle, here I am writing the angle, here 360 into your f. Now to see this, I will show you one example here, and this example here it says that, this example you can see how we can calculate. This is that your the change, this Vd, the link voltage per pole, it is 200 kV. It is given to you. It is also given here your the rated current ID n, it is your 1.8 kiloampere. It is also given your S22 here, it is 10 kiloampere. Frequency here it is given to you, it is 60 hertz, and your gamma n is given, it is operating at 10 degree, and gamma m is given, it can go up to 5 degree here, and then you have to calculate the value of L based on that here, so that we can avoid the commutation failure. This is the VD, this link voltage, this is a 200 kilovolt operating per pole. Here this current is the DC current which was flowing before this voltage collapse. This is the value here which is based on the calculated this value, and it is given to you instead of giving EM and omega and L values here, it is 10 kiloampere. And now the frequency of the system is 60 because we are going to use here, this is operating the AC side system, and gamma n is this value where it is a normally if there is no voltage collapse, your gamma n it should be commutation should be over by this degree. But we can go up to 5 degree. Normally if it is 10 degree, so it is 15 degree or so, but it is given to you. Now we want to calculate. Now from here the beta n is not given to you, and beta n we can calculate from this expression. Means it is given here, this value is your 1.8 here into 10, because this is a kilo, so it will be cancelled. Here your cos 10 degree minus cos beta n. So your beta n will be, that can be calculated, and as per my calculation it is coming out to be 36.4 degree. Now if this is known, now we want here in this expression this change in ID. Now you can see what is happening. To calculate the change in ID, which is very important, this expression which we are writing, when there was no collapse, we can write this expression here as here IDN d beta plus ID gamma by 2. What is happening? If the DC current is constant, whether at this value or this value is the same. So we can say this IDN divided by 2 is IDN. This I am going to write here IS2. Now here cos gamma, here I am going to write m value, because we are going to change, it is certain, it is changing up to gamma m, here your cos beta n. We are taking the average here because it is linearly increasing the current. So this why just by taking at the beta instant and the gamma instant taking average, that is the ID, it is going to be ID.
It's gamma n.
No, this is the gamma here at this value, yeah. Basically the gamma n is there, but now we are going to take here, that is approximately here, this is going to change here. What I am going to say here, this at the beta n, the current is your IDN. At the gamma m, I am going to take here, that is your IDN plus change in your ID. So this value here is n, and here we are talking n. Sorry, m. Here we are talking m. Now, if you add this, which equation? Yeah, this equation what I am doing here, if just assume there is no change in ID. So what we can do here, this IDN, at this n and this value delta n, it will be the same. Means we can write here this value, this where we are drawing the expression here. At this value beta here n, and whether any value here, gamma m or this gamma n, this ID was the constant. So this value was IDN, here also IDN, so we can write it in some way that it is a average of these two currents, which is if there is a small variation is there. So this expression here directly I am writing with this value. In the normal case here what is happening, we are having this is IDN because this is equal, and then both are divided by 2 means same value here. Now as per this expression what I am going to do, here we are just writing this, your I beta n here is your IDN, because at that time this was the current. Now your I gamma n here is going to be this current, because the current is changing here due to the voltage collapse. When there was nothing, it was not collapsing, this was 0, and this duration is very small, we can take the linear increase. So from here you just add it, it is your I beta n plus I gamma n m is equal to here twice IDN plus your ID here. If I can divide by 2 here, by 2 here, by 2 here, this expression here we can put it here. So the change of current, which is linearly we are assuming, it is your IDN, it is nothing but your twice IS2 cos your gamma m minus your cos beta n minus twice of your IDN. Similarly, this is 2. Here we are just putting this value, and this we putting that side, so going the here and divide by, multiplied by 2. So we are going to get this, means this current change due to this value now here is a gamma m rather than gamma n, because we are assuming the value is changing. It is said that the voltage is collapsed, and that's why the current is increasing, and the current increase is a linear one. So ID can be calculated from this expression. Now you can just use this value here, 2 into your 10, here cos 5 degree minus cos here 36.4 degree minus twice into 1.8. I put this value here, IDN, the normal current before the collapse, it was 1.5 kiloampere, twice here, the beta n we calculated here, and the gamma m is given to you is a 5 degree. If it is going, commutation failure will be happening. So it should be over by this period. Now from here, if you will calculate, and this value is coming to be here 0.2277 kiloampere. Means current is going to be 0.227 kiloampere is going to happen. Now this is now known. Now in this expression, this is given to you. This is said it is going to be 0 collapse voltage. Earlier it was operating at the 200 kilovolt, voltage is collapsed to 0. The maximum fall will be 0, it cannot be negative. So we are just considering the extreme condition. So this change in the voltage is 200 kV. So and then we have to calculate here this value from here, delta T. So now I can remove this and we can put this value. Now what will be the delta T for this one? Here it is your delta T will be 36.4 minus 5 degree divided by 360 into your 60. This will be some millisecond. It will be 10 to the power I think minus 3 second, and this value as per my calculation it is coming out to be 1.45 here, 1.454 second. Since it is in degrees, so I am using here 360. Means this expression I am using, and here 60 hertz AC system is there. So now here your LD I can write here 200. This is in the kilovolt, so it is 10 to the power 3 multiplied by here 1.454 into 10 to the power minus 3 divided by this value is your 2277 into 10 to the power 3 kiloampere, and this value will be your H. And as per my calculation here, this value is coming out 3125 Henry. So if can put this value of 1.3125 Henry, then we can avoid the commutation failure, even the voltage collapse to the 0 in the DC side, assuming that your AC side voltage is constant, inverter AC side voltage, and the current is linearly increasing, and for given this value of your gamma m, the 5 degree. So here it is, now you can see this very high value of smoothing reactor is required to avoid the collapse. Yeah.
If VD would collapse to 0, then why would EM would be constant?
The collapse cannot be even the only due to the AC side. It can be due to some other region. The collapse can be a converter side, can be a fault, can be anything with the DC side voltage can collapse. So we are assuming this AC side because the AC side voltage is not a radial system, it is interconnected by some AC system as well. Means you can assume here how the system is working. This is your converter circuit, rectifier, this is your DC link, this is your inverter, here this is your 3-phase, here 3-phase. This is basically complete system which is here, AC system is there, so all both sides. You cannot make this voltage 0 here because this is voltage is governed by some other AC system as well. So it is assumed, no doubt this cause may be voltage collapse due to this here. If the 3-phase short circuit here, voltage will be 0. But there are so many other conditions this voltage can be 0 due to this side, due to this short circuit or some other problem. So we are saying here that there is a voltage collapse. Yeah, sometimes the bypass valve is fired. Here there is a bypass valve, it is fired, it is voltage 0. But here the voltage is minimum. So this is a condition, that's why it's all calculation which I am making. Assumption that your EM is constant. If EM is going to reduce, what will happen? Let's suppose your IS3 here, which is a constant, this value is going to also reduce it. Once it is going to reduce, you can see what is going to happen here. This value is going to reduce. Once it is going to reduce, this is going to be further reduced. And once it is reducing, means current change is less, and current change is less, commutation failure will not occur. Because the commutation current increase is only trying because current is increasing and then it is leading to another side. So if that's why it is the worst case calculation we are doing. Otherwise what will happen? This value will be suddenly, you can see this IS2 is changed, let's suppose. You have to change here value and then you can calculate, no doubt about it. So accordingly here instead of 10 it will go down, this current change will be also reduced and therefore your commutation will be considered in that value.
But LD will be increasing.
Yeah, LD at that time it will increase, yeah. Inductance, high inductance value will be there. But this inductance value here it will be increased. This voltage is 0, this is T, this is ID. If ID is less, basically this is naturally here this LD value will increase.
So whatever design will not be valid in that case. We require higher inductance.
Yeah, we require the higher inductance and then how it is going to affect. Even though let's suppose there is no change. So this is 0. So LD is infinite. What is the meaning of LD infinite? You don't need anything basically. So here basically this is the case, ID will be of course 0, but if this value is less, you know the designing the small inductance is difficult than the larger inductance. Here the size, if you are going for the milli here and the winding, the number of turns etc., because n square upon r is the inductance value. So here this number of turns, r reluctance you require, what is the reluctance value? Approximately we can say this, what is the reluctance value? This L is proportional to your n square over the reluctance value here, equal to here. So for the given terms here, the reluctance value, if you are going for larger, this value will be smaller. Smaller means any small value you can use, or you can say any magnetic material you can use. But only I can say if the current is not increasing, means there is no sense of calculating this, means there will be commutation, there will be not a commutation failure at all. If there is huge change, you have to go for this because the voltage rise will be very high. Now, so now move to another protection schemes of the valves, that is called the damper circuits. The damper circuits, basically there is 3 types of damper circuits are used. One is the damper circuit that is due to the voltage oscillation, another will see due to the current oscillations, and another is called due to the line oscillations, line current basically oscillation. Why it happens? Now just you can imagine, before this valve is going to conduct, it was having some voltage. For example, let us see this diagram you see here. At this point, once you are delaying it, this is the valve voltage of any valve. Here, if you are firing at the 0 degree, the voltage across that valve is 0. Means here you can see at this value, it is just its commutation voltage is increasing. Means that's at this value it is 0. But once you are delaying, the voltage across this is going to be positive and more positive. and once you are igniting it, suddenly it is becoming 0. Now you can imagine there is some voltage before, and there may be some stray capacitance between the valve, because one is here the some polarity, another is some another polarity. So there is some capacitance will be formed, and due to this capacitance, when you are keep on increasing and you are firing here, this inductance, this capacitance along with the transformer here, that will be coming into series, and that will be the voltage oscillation. So this is basically due to this voltage across the valve. Once the capacitor is charged, it is going to discharge through your, once it is fired. The capacitance which was across the valve here, it was just some voltage was there, and the capacitance here some fixes. This you don't worry, this I will talk later. This is basically damper circuit we are putting. So here the some voltage across this is appearing, and now this is now fired. Now the charge which was here, it was the positive here at this cross, that it will be charged here. And due to this, there is some voltage here going to appear across this, even though there is some inductance here also. Again, this strict capacitance is larger. It is not only across this, here the inductance of the transformer is also there. So the capacitance here also there from the another side of the transformer. And this will be some here due to the, once it is conducting, so some discharge here of the voltage is going to rise. And that is called the voltage oscillation. No doubt this value of stray capacitance is very small, and the frequency of the oscillation will be very high, but magnitude will be less. We will see much more detail here. So right now I am talking about the voltage oscillation, and to minimize this we can use some damper circuit. Means that oscillation, if it is passed through somewhere some resistance circuit, then this oscillation will be damped out as usual, and it will go in the resistance and the resistance will be basically lost, and finally it will be damped out. The major problem in the voltage oscillation is there is a possibility that it can be the arc back may occur. Means it can conduct in the negative polarities here. So if you are using the valve dampers, then it can avoid the frequent arc back, the basically conduction in the negative voltage side. It also, damper circuit limits the rate of rise of inverse voltage. It reduces the peak inverse voltage in the mercury arc valves as well, and it avoids the breakdown of the inverse voltage exceeding the rated value. We saw here in the ideal case, the voltage rise is sudden. In the valve voltage which I explained you, here in this, here you see, whenever you are just, there is a voltage is here, sudden jumps, whenever there is a conduction of any valve is taking place, the jumps are there. But in the practically it is not happening, because there will be some capacitance, some inductance, some circuit, the stray capacitances and this your inductances were there, and this rise here, rate of rise is infinite, because in 0 second the voltage is changing, so certain dV by dt divided by 0, it is infinite. But practically it is not infinite, it has some limited value, but it is very high, no doubt, and it is very high. So we can use some damper circuit so that we can minimize this, because at this point there is a jump and possibility of in the inverse voltage it may conduct. So what happens if it is conducting in the inverse voltage here, that is called arc back is there. Also there is a possibility here at this point, the voltage across this is there, and due to this oscillation we will see the current oscillation will be also there at that time. So there is a possibility of the misfire. This is here, and current is going to reduce due to that oscillation of the current in the valve due to the charging here. So these are the jumps, and these jumps are very dangerous. So we have to use some damper circuit so that we can minimize the oscillations, and also we can, the sharp edges we can reduce it. Now you can see what will be this voltage. This voltage we can simply, before that I think we can just see some theory here. As I said, this oscillation of voltage you can see 10 to 20 kilohertz. Why? Because these stray capacitances are very less, and frequency you know, this is 1 upon LC. L and C both are very small, and therefore it is, this value is, frequency is very high. So it is in kilohertz, and but the problem here, the overshoot is sometimes is 10%, 100%. So voltage is going to be double. And even though it is a short duration, it may cause damage, or it may cause your valve should conduct in the negative direction. So that's why it is said here the arc back here, it is a possibility here the arc back may happen due to the even though stray capacitances. But if you are using this dampers, then it is going to minimize this. Now you can see here, so rate of rise of inverse voltage is finite, but in reality it is not so due to the stray capacitance, as I said, across the valves, because the capacitance is formed because the voltage is appearing. And once voltage from the two terminals, conducting terminals are there, and then some capacitance will be automatically, because the air is as a medium, it is formed. And already I said here this value, satisfactory rate of rise voltage can be obtained by connecting a capacitor across each valve. If you are connecting a capacitor, suitable value of capacitor, then we can reduce to 1 to 2 kilohertz. And but the overshoot you cannot reduce, overshoot is 100%, and to minimize this you have to connect a resistance in series with the capacitance, then your overshoot means the damping, the overshoot will be also reduced. So that's why we connect resistance here in series with the each capacitance, and this is called your RC damper, or it is also called the valve dampers, because we are using across the valves. Another advantage of this, the damper circuit, if you are using the damper circuit across each valve, if there is any transient across this voltage, this is going to share across other valves as well. For example, here you see here, if there is any transient occurring across this voltage is going to here and is going to divide by this circuit here. So it is not only limited to that valve, it is going to divide it in other valves as well, and it is a safer one if any transient occurring across any valve. So this is also, that's why it is said here it is going to safeguard. It's a division between the two or more bridges where the valves are there, it will be just going to be shared. But only problem here that it is, if you are using some resistance, it is going to be lossy, and thereby the efficiency of the system, because the loss is coming from the area. Wherever this R is there, and even though the stray charges are there, it is going to dissipate it in the resistance, and finally the efficiency will be reduced. And that is again it depends upon your design, what is the value of R, how much it is the stray capacitances are formed, and based on that these efficiencies are calculated. Now in this circuit I want to see there is a two voltages that is to be calculated. One is this voltage. This is the voltage when the valve is going to be off. If you are trying to draw the valve voltage for valve 3, at this point from here to here it is going to be off, and this value is delta. Means what is happening, your this value, here I should explain here. You can see this is here at this value some alpha is delayed, and then your U period is there here. Once commutation is over, then this valve 3 is off, and your fifth is taking care. This is a 3 to 5 commutation, if you will say. So this value, if you will see what is this value, the magnitude, you can say this magnitude is nothing but under root 3 times sine delta, because this is a sine curve. This is here, it is a sine curve. No doubt this, I am talking magnitude. No doubt it is a negative side, I am talking how much jump is there. What is this value of magnitude here? It is, I can say VJE. Vj I am talking the jth valve at the extension of this valve. Means when it is going to be off. I is used here when it is going to ignite. So this value you can say this is a sine curve. So this value is from here 0, if you are taking this is axis as 0. So this value will be sine delta, and this is your line to line voltage. So under root 3 times EM is appearing, and this is your voltage. Now this voltage, you can see it is your commutation voltage here is starting at this point 0, and we are going to fire here. This is alpha degree delay, and this is again sinusoidal. So this value your will be under root 3 em sine alpha. So this magnitude here we are talking, this is your this value, and this value here I am talking, this is this value. So these are the highest voltages, those are going to occur. But we will see some other voltages, like in between here, this is another voltage jump, here another voltage jump, here we are having another voltage jump here as well, and we are having here as well as here. So we can also see why this value will be here, it will be the equal to this value, and these three here, here and here, they are equal in the value. And it will be because at this time the valve is going to extension, some valve will be going to extension. So this value will be your VJE by 2. How? We will prove it. Another is whenever you are going to ignite any valve here like this, like your this and like your this, it is equal to your V. This is not this, is by 2 you will be this, VJI by 2 will be there. It is for this term, and we will see why it is so and how to calculate this value, why it is half, why not full, and we will just see from this diagram, we will calculate. Got it? But here we are saying simple RC circuit, not diode, nothing. But some circuit will have the diodes also, because it will increase the back peak inverse voltage capability of the diodes, thyristors. So now I want to calculate what will be this value here. Let us calculate at this value first, this value here. Now this value that we can see, you see this is a one curve here, means this value is at this point, this minus this we can get, means we can write this value, what is the instant here, starting as this as a 0, this magnitude here at this point, it is your under root 3 em by 2 if it is a peak one, but it is not a peak value, it may be before also, it may be after also. So what we will do here, I want to write this value here, I can say A and here it is a B, it is clear, A. So at this voltage A will be your under root 3 em sine. Now what is this period from here to here? Here to here, basically at this point is 60, it is your 60 plus delta, okay, because this is 60 because we are firing here. So it is 60 plus delta, because this delta here it is a 60 plus delta will be there. Now minus, I want to write this, if you see this voltage wave shape, it is your 1.5 em, this value it is written here, maximum is 1.5 here, this peak. Now it is sine, you see how much value we are going to at this point here. You see first we are taking this as 0, mind it, its 0 is somewhere here. So this is basically the 30-degree shift, because this is 30 degree, line to line, this is a phase voltage. So this is 30-degree shift. This plus it is 60 plus a delta. Simply this is a 30-degree shifted, because we are here taking at this point as a basis. Yeah, so this is your value. Now this value is 1.5 em here cos delta, because 60 plus 30 is 90 and 90 plus delta is your cos here, and just expand this value. So this value you are going to have under root 3 cos em here sine 60 into cos delta plus under root 3 em cos 60 into sine delta. Now you will find here this value and this value here is going to be cancelled, because sine 60 here under root 3 by 2, so under root 3 will go, so 1.5 here it will be cancelled here. So we are having this value only, and this value here cos 60 is half. So we are going, and this value you can say this, so we can say this value is your VJE divided by. So your all these values here, whenever it is going to extension here, this is the highest value, and other values are here, this and this are of half of this. It's proved. Similarly, we can see if this is a VJI, all these values, this side, this is small, wherever you are going to ignite, this and this will be of half. Similar concept can be applied. So you can, again, you can see your, I can write for any value here, you can take for this, just it is a plus alpha degree here. So this value your, I can write, now I am writing for here. Here is looking, actually,
plus alpha.
yeah, I am talking here at this alpha value here. What is this value? So yeah, 60 plus alpha here of this peak, this highest value, that is under root 3 em sine alpha plus 60 minus this 1.5 em, again 30 plus 90 plus
Plus
alpha,
alpha.
and you will again then prove it, you will find it is a half of this value. So at extension, no doubt this value looks, it depends upon how much alpha you are delaying. If alpha is larger, you will find this value is increasing, but if your delta is more, this value will be always larger here, because this is a alpha plus your value is u. So this will be always larger than this. You are delaying this is also delayed, and then this more value. So these jumps are very, very critical when your valve, any of the valve is going to be extension. So this side, when it is extension here, 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 and of course of the same valve here, the voltage is going to change. And these are the critical conditions, and using this RC damper circuit here, you can see we are using R here and C, and this is also called your valve dampers, because they are connected across the valves. Now another here we use, that is anode dampers we call it. In anode dampers here, if the ignition of the valve is delayed, a positive voltage is built up across it, which collapse when it is ignited. Again same concept is there, but it is, since it is, then it will be discharged through the valve. So current oscillation is there. So in that case here, there was some capacitance was there, and it will be not oscillating unless until you have some stray inductance. In that voltage circuit, we were taking the inductance of the transformer that side, and voltage was appearing. So voltage can oscillate, current also oscillate. So here basically current is, once it is conducting, it was charged, and then it is going to discharge here through this, and the current is going to be added on your ID DC current. So it will be sometimes negative, sometimes positive. What happens, sometimes current is going to be very negative, if this value is very high discharging, so the current becomes here 0. So you are just giving a firing pulse, it is igniting, but it will misfire, means it go, and it will be, you can say arc quenching may happen. So this is basically happening, the stray capacitances, and if there is some inductance strays are there, then now this value is again very, very small. The stray capacitance are very high, sufficient amount, but the inductance is stray strengths are very, very less. So what happens, its oscillation, you can say it can go in the megahertz, is very high value. So it is starting here, that was 10 to 20, now it is 20 to 10 megahertz due to this, because this inductance value is very, very small. So, and you know, this is a lightly damped, because there is no resistance involved here. Normally the resistance here, stray resistance are very, very small. So it is very lightly damped, and it is going to be very high value here, detrimental. So what this does, due to this, the current, once it is a oscillating high harmonics, so that may affect your radio interference nearby the communication signal, it will be affected. Then there is a possibility of arc back of outgoing and the misfire of the same valve. So these are the detrimental effect of this current oscillation, and then we use the damping circuit, and that is called anode dampers. And anode dampers, you can see what we do, we use some sort of circuit here, like we use some circuit here, you can see we are using here this some damper circuit. See this figure, what is happening, this you see here it is written this the power frequency of the valve current here, this is changing here, the valve which is ID which is flowing across this. Why this is looking linear? Normally if you see the current increasing in any valve, it is going to be like this, but we are talking here in the millisecond. So very small value. So this is just like a linear circuit is shown it to you here. Due to oscillation, here you can see this very high value of oscillation is added, and here if you are not using any inductance here, if you are not using any inductor in series with the valve, then here you are getting a very high oscillation. But if you are using the anode reactor here, we are using anode reactor here, what happens? You can see the current is going to be this frequency is reduced drastically. So what happens? Now your current discharge is going to be here, this circuit. Just remove this R. R will be used later on to avoid the more loss so that we can release the energy. So if you are using this, then your frequency going to be this. To simplify this, this figure is now translated here. You can see this is a linear circuit as a D here, and if you are not using any resistor here, then your oscillation is your B with anode reactors. Basically this is a reactor, this is just like it is rising on this current. This is oscillating, which current is taken care by this valve, and on that it is oscillating. So this is basically current which is taken by, let's suppose, I3. Over this is due to this, once it is ignited, and it is going to be here like this. So this is, you can say, it is a lightly damp, and this magnitude is not reducing, very less reduction is there because there is no resistance in this circuit. Some resistance offered by this valve may be there, and that is very small value. Now if you are using, so what we here it is suggested, we cannot put a resistance in series of this valve because huge current is flowing. We cannot put here resistance because this is a stray value, we don't know where is the connection. Because these are the stray value, it is not a physical inductance, it is not a physical capacitance, it is a form between the 2 points here. So this you are using inductors to damp out. Here the frequency is here changed from here very high value, now we are going to less value. So if across this we are using here resistor, because whenever the voltage is going to be here, voltage across this is coming and the loss will be coming here, and now you can see it is going to be critically damped. And this is called your anode damper because you can say it is connected anode across this wall or thyristor. And this, since damper means you are having some damping circuit, that is you should have R, that is a damper. So we are using L and R, this is a reactor and a resistor in combined together, and this we are getting here to value. So this is your anode dampers are used to avoid the oscillations etc. in this circuit. Another dampers we used, that is called the DC line oscillation, or we call it the line dampers. Why it is happening? Now already you are having a smoothing reactor in series with the ID, and the two poles or even the one poles having the zero potential and high potential, capacitance will be formed. So due to this there is some oscillation because the stray capacitance is formed. Already inductance you are having in the DC line, and then there is some oscillation will be happening, and this is called the, you can say, and this is basically the due to the different region. If the DC current is constant, then there will be no oscillation. Why? Because this is DC, inductance is 0 for this DC, and this capacitance will be there. Whenever the voltage changing, the DC voltage, either step voltage or something, then this here this voltage across the inductance is going to change, energy stored across the inductance is going to change, and once it is going to change, it must be exchanged through the capacitance. Because inductance Li square energy you must know, if I is constant, this energy is stored in the inductor, capacitor is charged at the same, here the voltage, whatever the voltage is there, and there is no exchange of the energy. If you are changing here the voltage, capacitance voltage is changed, stored energy is going to change. So if energy is changed, means this energy must be discharged through some other device, and this is your inductor, and once it is going to discharge through the inductor, then there is an exchange of energy. Once there is exchange of energy, means you are having oscillation. Always oscillations occurs if you are having the two type of storage devices. If you are having simple capacitance, there will be no oscillation at all. So you must have an inductor and capacitor combination for the oscillation. So that's why we every time we were discussing the inductor and capacitance. So there is a possibility that voltage is changing. There is a possibility the current is changing. If current is changing, mind it that voltage is constant. So capacitance energy is constant. Here inductance energy is changing due to the current. Then we again oscillation. Another, if your voltage is changing, current even though constant, then again it is going to change because your capacitance energy is going to exchange. Or both are changing, so it is happening. So that's why the three cause, if your voltage is changing, alternative side here, this voltage of DC output will change. Or there is some step voltage is arising due to some other misfire or fire and other thing, then this may also go there. And if it is a short circuit, the current is changing, then these are the three causes of the line oscillation. Now here there is a different the possibility why it can happen. Now the voltage change basically due to the block, if your main valve is blocked or misfired the bypass valve, etc., fault is there. So it is, these three conditions: AC voltage changing, then it is reflected on the DC side, or step change due to the bypassing of the valve, or due to the misfire, due to the commutation failure, always there is a step change in the DC output side, or even the DC short circuit current. So these basically the conditions may arise, and that is a giving your oscillation in your line here. So that's why the voltage change here, if you are starting the rectifier or bypassing or unbypassing the bridge, recovery of the AC fault, these are the various basically causes, that is the step change will be there. So how we do, the damping can be obtained by using resistors across the smoothing reactor and or the stray capacitances. Means here you can see this is your smoothing reactor, this is your stray capacitance. So to avoid the to reduce the damping here, or you can say provide the damping, means you don't want the oscillation, here we can use some resistance here parallel to this, or we can use the resistance across this. So what happens if it is a discharge, it will try to discharge here itself. If there is some energy here, it will try to flow in this one circuit loop itself, and it is dissipated in the air and this will be there. But the major problem here, you can see if we are using this R, huge voltage across this resistance is there, and even though in normal condition this loss is there. In the normal, the DC is constant, and then it is still there is a huge voltage and the resistance, the huge loss is there. So what we put? We put a capacitor here. If it is a constant DC, there will be no current. Whenever there is some oscillation, then this will provide as a filter and it will be oscillating here. So here this is a RC damper, that is called the line RC damper. We are using the lines here. This is a line, and then we are the grounding it here. So this is a RC damper here. We use the capacitance. But the cost of this capacitance is very high and the large. To avoid this, if you can use the inductor here, then here you can minimize the cost of this quality capacitors. And here if you are using this, then this is called your LCR dampers. In this condition, what happens, some harmonics current if you are using here, this C, then it can also flow. Similarly, if you will see here resistance, if you are putting across the resistance here, always there is some change. This, even though there is no line oscillation, but due to some small change here, that is not available, there is some loss here. Because the current slightly changing here, the huge voltage here arising, and that is going to be there. So what we do, again we put here capacitor in series, so that in normal condition, if a small value is there, so there should not be discharge, and we put the inductor in series to avoid minimize the cost of this capacitor. So that's why to reduce the size and cost, inductance are used. So you can say here LCR damper here also we are LCR damper. Some people propose here in putting in the instead of series, we can put in the parallel. This is another tuning of the capacitors that can be used. So this is your line dampers are used to avoid the discharge of this the line oscillations. So at the end here in whole this module, what I discussed, I want to summarize here. In this module we discussed the following things. We discussed the various type of faults, including even though AC over voltages, AC over current fault, etc. Then we talked about the mal-operation of converters, including your arc back, arc through, misfire, and more detail on the commutation failure in inverter side. Because the commutation failure is a very common, and all these faults will lead to your commutation failure in the inverter side. But the rectifier side, these misfire, arc back, and your arc through files are we discussed with the voltage wave shape, and we saw how it is going to happen. Then I discussed the various protection schemes, how we can use the over voltage protections. We also use the overcurrent protection that is done by the valves itself control. Here the over voltage, we are using over voltage protection as well. And then we also saw we are using the differential protection to check the pole current dissimilarities. And I give a complete layout how the protection schemes for over voltage as well as your overcurrent and differential protections are used in the converter stations. Then at the last lecture, I just discussed the various damper circuits, and including your valve dampers, basically valve dampers, anode dampers, and also the dampers those are used for the line oscillations here, that is called your line dampers. So this whole module was basically related to your faults and protection and the mal-operation of converter circuits. With this, I can end this module number 4, and we'll see in module number 5 the different aspects. Thank you.